This section is about pH curves. We will be doing quite a bit of lab work around titrations and the titration curve. So let's take a look at a titration curve to see what it looks like. What you're doing is you're plotting the pH of the solution as a function of the amount of titrant added. Titrant is that which is added to the solution to change the pH and to neutralize it. So sometimes you are adding an acid into a base, and sometimes you're adding a base into an acid. The equivalence point is the point at which you've added enough of the titrant to react exactly so that the amount of hydrogen and the amount of hydroxide are equal. Here is an example of a titration curve. You will notice two things. You will notice it's a very gradual increase as we move along, and then suddenly there's a huge change in this small area. In other words, from this amount of titrant to this amount of titrant, NaOH in this case being added, you'll notice that the pH changes in a huge amount. The equivalence point in this example is 7. And you can tell from the picture, because the curve is so sharp and it goes up so quickly, it must be a strong acid and a strong base. Now if you read up here in the purple, you can see it says the pH curve for the titration of 50 milliliters of 0.2 molar HNO3, so that's what's in the solution, and the NaOH is titrating into it to neutralize it. We have a strong acid and a strong base, and of course you can see the pH is going to be 7 because it's going to be neutralized at 7. The salt of that which is being produced, the sodium nitrate, must be a neutral salt in water, and therefore its pH is 7. Here's another example using NaOH and HCl, both strong, one acid, one base. Again, the equivalence point is happening at 7. Notice again the very slow gradual change in here, and then suddenly a huge drop. Sometimes after just one drop you can have a huge change in pH when the thing is neutralized. In this case, we're starting with a base which has a high pH. We are adding an acid to it. Eventually it will become neutralized, and of course when we add excess acid, in this case you can see in the bottom here, the pH changes just a little bit. So in the very beginning and actually in the very end, we have a bit of a buffering effect, and that's why it's kind of flat in those areas. So let's look at a weak acid and strong base titration. So in other words, we're going to start with a weak acid, and you're going to add a strong base to it. How do we solve these kinds of problems? Well, we have first a stoichiometry problem. The reaction is assumed to run to completion, and then an equilibrium problem, or ICE, to determine the position of weak acid equilibrium, and then we're going to calculate the pH. That's what we do every time. Right. So this is the example I think I was referring to before, where this particular set of PowerPoint slides actually doesn't give you an answer for this one. So we're not going to work it out. But it does say, consider a solution made with mixing 0.1 mole of HCN, there's its Ka value, with 0.04 mole of NaOH in 1 liter of aqueous solution. What are the major species immediately upon mixing? That is, before a reaction. You will notice, just like before, the major species are made up of those things that can ionize. HCN, which I know we've had in an earlier chapter's PowerPoint, is weak, obviously has a Ka value as listed here, doesn't ionize, therefore it stays together. Sodium hydroxide, however, is a strong base, and that's why you see Na positive and OH negative, and of course water. So why isn't NaOH a major species? Well, of course, it breaks apart into its ions. It doesn't stay together because it's strong. Why aren't H plus and Cn negative major species? Again, that one's weak, and therefore it doesn't break into ions. So we're going to list all possibilities for the dominant reaction. Now, in reality, we don't really need to do this, but I'm going along with the book, and so this is what they show you you're going to do. Here they are. There are 5 of them in this case. Well, we have the self-ionization of water is the first one, HCN in water, HCN in OH, NaOH, which is a strong reaction, probably should only have a double arrow, and of course Na and water to produce sodium hydroxide and hydrogen ions. The one that we're really going to use is actually number 3. How do we decide which reaction controls the pH? Well, it's the one that's going to have the major contributor of the hydrogen or hydroxide ions. And of course, there it is right there. Usually you don't have to go through this. If you're doing a titration, you're going to have, in this case, a weak acid and a strong base. You notice I didn't have to put NaOH here. I'm just putting the OH negative part of the ion because the sodium ion doesn't have any acidic or basic properties because it comes from, NaOH. These alkali metals don't have any acid or base properties, so we just use the OH negative. What are the major species after the reaction occurs? Well, again, what are the major species? The ones you see listed here. HCN, Cn negative, and that's because it's here as a product, HCN. We've got Na, which is part of NaOH. And you might say, well, where's the OH? Well, actually the OH is used up and goes away to produce water, which is one of those products. You'll also say, well, I don't see the Na in the beginning because it was a spectator the entire time. So really, although they list it here, it is a species afterwards. It's not an important species, so most people don't even list it. So you can treat this situation as before. We're going to list the possibilities for the dominant reaction. We're going to determine which controls the pH, and then we're going to do some problem solving. So let's look at an example here. All right, calculate the pH of a solution made by mixing 0.2 moles of acetic acid with 0.03 moles of NaOH in 1 liter of aqueous solution. So let me show you how I would do this problem. And I wouldn't have to go through all the painful little steps that we had gone through before that your book likes you to see. So what I would do is I would know that HC2H3O2 is a weak acid. And it's being titrated with the base NaOH, which is a strong base. Again, I'm only going to use the OH negative. And I want to make sure that it is acting like an acid and a base. And of course, an acid is a proton donor, so I'm going to, this hydrogen will go over there and form water. The other product is C2H3O2 negative. All right, now I'm going to, because it's weak, I know I'm going to use ice, so I'm going to write that out. I also am very lucky in this question because it's in 1 liter solution. Because it's in a 1 liter solution, I don't have to worry about worrying about the molarity because the moles and the molarity are the same. So I'm going to write, after I erase that dotted arrow, I'm going to write this is 0.20 molar. And the NaOH is 0.030. We don't have any products like a buffer in the previous section. So we have this reaction. We assume that this reaction goes to completion. So we have to look at the reactants, and you can see that the ratio is 1:1 on all of these acid-base problems. And we want to make sure that the limiting reactant is used up. The limiting reactant in this case is the OH. So the change is -0.03, minus 0.03 plus 0.03 plus 0.03. So now we have 0.17 moles. We have 0 of this. We don't really care about this, so I'm not going to write it, although we'd have 0.03, which doesn't matter. And we have 0.03 molar. I shouldn't write moles, I should write molar of that one. Now we actually have something to use kind of like a buffer. Could we use the Henderson-Hasselbalch? I'm sure we could. I'm just going to proceed on and show you another alternative way to do it, thinking about stoichiometry, after using stoichiometry, using equilibrium. All right, so we're going to look at this, and we're going to see what is the major, so this is equation number 1. Equation number 2, what is the major contributor of pH here, of those things which we have left, this or this? Hopefully you're saying it's the acetic acid. So I'm going to write this one acting like an acid, and I'm going to ice again. You might say, wow, there's a lot of icing happening. 0.17 molar. This is 0.03 molar, and we don't have any of this. Minus x, 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 0.17 minus x, x, and 0.03 plus x. I'm going to come over here on the other side, and I'm going to solve this as a traditional Ka problem. In other words, x, 0.03 plus x, 0.17 minus x equals the Ka value here that they give me right there, 1.8 times 10 to the negative 5. When I solve for x, I got 1.02 times 10 to the negative 4. That makes my pH equal to 3.99. And let's check it out if we're right. Let's see if I think they walk us through it. But that's how I would do it. Let's see what they do. They are listing the major species again. No problem with it, but I don't do that. We all know why NaOH is not a major species, because it ionizes 100%, and of course the hydrogen and acetate ions are not major species because they don't ionize. So they're really trying to focus in on what ionizes and what doesn't. And they look at all these reactions. Again, which one really happens? It's the one that controls the pH, which is the third one. How do we know? Because it's the one that is going to be the dominant producer of the ions that cause the pH. All right, we're still thinking about it. Ah, good, there we are. Now, notice what they did, just like I did earlier. I used 0.02 and 0.03. We made sure that OH negative is used up. And we have a little bit of acetate and a little bit of the acetic acid. We could use the Henderson-Hasselbalch equation here, but I did not this time. They're showing this equation having a K value of 1 times 10 to the negative 9, or to the positive 9, pardon me, because they want to show you that this goes to completion. That's all they're doing there. You don't have to do any equilibrium problem solving. All right, now we're going to solve for pH. We rewrite the equation. They're showing it this way, just like I did. And they're using 0.170 and 0.03 and the same minus x plus x. We're going to solve the K. There's the Ka value, and when you solve the pH is 3.99. So a very traditional equilibrium problem. But because we have reactants and products, we can use the Henderson-Hasselbalch. All right. Let's look at this example, and here they want you to calculate the pH of 100 milliliters solution of 0.1 molar acetic acid, which has a Ka of 1.8 times 10 to the negative 5. I've used this acetic acid so much in this last 2 videos, I feel like I have memorized the Ka value for it, but luckily for us, it will be provided. All right, so how do we do this? Well, nothing's been added. It's just plain old acetic acid. So we have HC2H3O2 forming its 2 ions. Not well, though. I'll remind myself by putting the double arrow. Sometimes I forget that. and it's a 0.100 molar solution. And the fact that there's 100 milliliters is nice, but it doesn't matter because it gives us the molarity. And we have no products. So this is just like the ones from chapter 12 and 13. 0.100 minus x, x, x. So x squared over 0.100 minus x equals 1.8 times 10 to the negative 5. When I solved this, I got my x value to be 0.00134 and my pH value to be 2.87. So let's see what they tell me it is. 2.87. All right, good job. So we're then going to do something else with this. That's the reason they give you this as the introduction to this. Now we're going to calculate the pH of a solution made by mixing 100 milliliters of the 0.1 molar solution of acetic acid, so the one we just talked about, and 50 milliliters of 0.1 molar sodium hydroxide. Now when we add a base to this weak acid, the pH is going to change. The question is, what is the pH going to become? So your book will want you to list the major species, figure out the dominant reaction, all of those things. But we already know we have acetic acid and we have OH negative, which is going to form water, and C2H3O2 negative. Now, we have some information here, and we have 100 milliliters of the 0.1 molar solution of acetic acid, and that's pretty nice. So 100 milliliters of 0.100 molar, and I'm writing it above to remind me what they are. This is 50 milliliters of 0.1 molar. All right. So you might think, why don't I just put 0.1 down under the acetic acid and the OH negative ions? Because this is where things get a little exciting. When you mix these two solutions, their volumes change. And the volume in this case is 150 milliliters. So in the beginning, when they're mixed just initially, the molarity of the two solutions that they give you in the question do not remain the same. They actually decrease. And for example, for this one, we're going to use MV equals MV. In other words, if I have 100 milliliters of a 0.100 molar solution, what's the molarity going to become in 150 milliliters? Because I'm diluting it a bit. When we work it out, we get 0.0667 molar. I do the same exact thing for the OH negative. I'm going to say 50 times 0.1 equals M times 150. When I work it out, I get 0.0333. And that's the molarity. Now, we know this reaction goes to completion. So the one that's going to be used up is OH. So minus 0.0333 minus 0.0333 plus 0.0333. And here this goes away. I get 0.0334. It's probably about the same number. And this is 0.0333. Now, I can go through and I can write the acetic acid as the major component, just like I did before, and producing hydrogen and hydroxide, and put the numbers in and work it all out using the equilibrium ice. That would be fine. We'd get a great answer. Same answer we'd get this other way. I'm going to do this one using the Henderson-Hasselbalch. The last time I did not, so I thought this time I would like to show it to you. pH equals minus log of the pKa, which is 1.8 times 10 to the negative 5, plus log this over this. Essentially, it's log 0.0333 over 0.0334. This is basically a situation where it's log of 1, which is 0. And so if we took the negative log of 1.8 times 10 to the negative 5, you would see it's 4.745, or let's see, and they get pH of 4.74. That's fine. It's probably just a rounding error on my part somewhere. So that's the idea. If you do this, I think you get really 0.001 or something like that. And it might add to it a tiny bit. But that's the idea of how to solve this kind of question. And then the last question of this section is calculating the pH of a solution at the equivalence point. That's where the hydrogen and hydroxide are equivalent. So when we have 100 milliliters of a 0.1 molar solution of acetic acid, which has a Ka value, that again, and it's titrated with 0.1 molar NaOH. Now in my previous reaction, HC2H3O2 and OH negative, remember initially I had 0.0667 as my molarity of the acid. It's the same situation here. But when do we have an equivalence point? That's when all the OH, or the concentration of OH, equals the concentration of the acid, such that we don't have any reactants at all. This has to be 0.0667. We can actually, if we wanted to, figure out when that would have to be. I think it probably has to be at about 100 milliliters. So in this case, we don't have any products. When we subtract 0.0667, this is 0.0667, we don't have any reactants at all. In fact, we only have products. So the major contributor of the pH is actually this, because it's the only thing left. I'm going to put it down here. So that means if I rewrite a reaction, C2H3O2 negative, and I'm going to, usually you react it with water in this case because it's easier to show. If this is an acid, which it is, this is the conjugate base. So we're actually showing a base reacting with water. Bases are proton acceptors, of course, so we get H, C2H3O2, and OH negative, and you can see the OH negative being produced. Now if you're very clever and you look here with what I just wrote, do you notice it's the exact opposite of the reaction I wrote above, right? It's this reaction essentially going in this direction. That always happens at the equivalence point. Now we have 0.0667. So we want to solve this question. How do we do that? Well, it's the old ice again. We can't use the Henderson-Hasselbalch because we don't have numbers on both sides. So we don't know the change, but we can calculate some information. Now, when we are solving x squared over 0.0667 minus x, it better be equal to the Kb value because this is production of a base. And I get the Kb value by using Kw and this number, and when you do, you get the Kb value of 5.55 times 10 to the negative 10. That's what you get for that. Then you solve for x. When I did, I got 6.08 times 10 to the negative 6. And that is the concentration of OH. So I could find the POH, because that's the easiest thing for me to do, POH, which I got as 5.21. And so the pH is going to be 8.79. Let's see, whoops. And they got 8.72. A little bit different than mine, but pretty close. It could be a rounding error on my part again. So notice if we show a picture of it, the equivalence point does not happen at 7. It just happens to be a little bit higher. Don't forget, you are mixing a strong base and a weak acid. And the salt that's produced is more basic. So you know that the equivalence point is going to be greater than 7. In general, as the Ka value decreases, the curve will look different. You notice for the strong acid, see how flat it is, a lot of buffering, and then a huge jump. As the Ka value gets less, this is a little bit more curved. You see, even in the beginning. In fact, when it's very weak, there's a kind of a huge jump right here in pH because it's so weak. You see that right in the beginning. So sometimes I've seen questions where they give you a curve and they say, is this a strong acid-base situation? Is this a weak acid, weak base? You know, what is it? Based on the picture. So be careful to understand that. I'll erase that so you can see that. This is just an interesting picture of the relationship between, in this case, a strong base added to different amounts of and different kinds of acids, either a really strong acid or a really weak acid. But we'll be doing lots and lots of practice of this, and in fact, right before the midterm, we're going to have several days of actually doing some titrations and analyzing our own pH curves.